ఏమైందిరా? ఏం కాలేదు కదా! ఆ! ఆ! నేను పెడతా. ఎంతసేపు పోస్ట్ పెట్టేది పోస్ట్ పెట్టేసి ఓకే. సీన్ 1 నుంచి పోస్ట్ పెట్టేస్తా. Okay. So yes. Now let's directly go to creating the other cube, other entangled states. So before the break, we have been seeing how we are going to create an entangled state by using a circuit. That is, firstly we applied a Hadamard gate, and after applying the Hadamard gate, then we applied a C naught gate. So the applying of Hadamard gate as well as the C naught gate will give rise to my 5 plus state, which is my first entangled state. Now, by using that 5 plus state, we can create other entanglement states as well, or other entangled states as well. So, how we are going to do that? Very simple. So, that is, so this gives rise to my 5 plus state. Okay. This gives rise to my 5 plus state. Now, if I keep the Z gate here, if I keep a Z gate here, then I'll be having a 5 minus state. Then we'll be simply having a 5 minus state. Okay. So I can create a 5 minus state by just simply providing a Z gate on my Q node after completing the circuit for my 5 plus state. After completing the circuit of my 5 plus state, the simple applying of my Z gate to my Q node will give rise to my 5 minus state. Okay. And the third thing, the psi plus. If you want the psi plus state, if you want to see the psi plus state, what we'll be doing, instead of this Z gate, you'll be keeping an X gate. Instead of this Z gate, if you keep a simple X gate, you'll be getting a 5 plus state. Okay. So one can get a 5 plus state by just using a X gate after applying all these operations. Got it? Now, if you want a 5 minus state, simply use a Y gate here. Got it? So if you apply a Y gate for my, what can I say, this 5 plus state, you will be getting a psi minus state. Got it? So in that way, we can create all the entangled states by using a simple circuit. Okay, I've simply to put, I can create all the entangled states by using a 5 plus circuit. Got it? So here I will draw everything or I will write everything clearly. That is, first thing is, well, we can write it like this. C naught had a mad gate with my, what can I say this as? 0, 0. Gives rise to my 5. Okay, 5. So for this 5 state, if I apply which gate, the gate which we discussed about is Z gate, then I will be having a 5 minus state. For the same thing, if I apply for the same 5 plus state, if I apply an X gate, I'll be getting a psi plus. And for the same 5 plus state, if I apply a Y gate, I'll be getting a psi minus state. So this is how I can get or I can build all of my entangled states by using the quantum circuit. Or I can say first I will create a 5 plus state directly, and after creating a 5 plus state directly, from that 5 plus state I can easily derive all these further operations. So all these further states. Got it? So in that way I can create an entangled states. Okay? So this is how I can directly create an entangled state. Understood? No. This all things comes under my bell sticks. Simply to put. Okay? Right. So what is the advantage of this bell stick? Simply to put. We have seen all those advantages, that, this and all, right? Now let's talk about one practical application called as super dense coding. Let's see how exactly this entanglement concept is giving rise to an advantage in quantum systems. Well, before going to this super dense coding, I will explain about one other thing as well. That is my classical bit representation in a quantum circuit. So in a morning session, I have mentioned you one. If I have something like this represents the presence of a classical bit in my, what can I say this as? In my quantum circuit or in my quantum environment. Okay. Now, how exactly I'm going to do that? For example, if I have an X gate and here I applied a Hadamard gate, and let us consider here I applied a C naught gate. Okay. Now, what exactly is a measurement gate? And simply to put, let us consider I am measuring Q naught. Let us consider I want to measure Q naught value. At that time, I will be giving something like this. So I'll be measuring by a particular qubit by using a measurement gate, and this output will be saved in my classical bit. Got it? So this is my classical bit thing. Meaning goes like this. So Q naught, some operations happen here completely already, which we don't need to care about. And suddenly we are simply measuring my Q naught. That's okay. So I also mentioned one point. When we measure a quantum state, it will be decomposed into what? Classical thing. So that's why once the measurement is done, the output is being stored in my classical bit, but not in my quantum state or something like that. Okay. Once the output is calculated or once I measure that particular quantum state, it will be stored in my classical bit rather than common state. Okay. In that way, I am finding the answer to my quantum state. So this is my measurement kit. Okay. Now, what will be the output of this one? Can anyone say that? So I measured my Q naught, right? So that Q naught measurement is stored in classical bit 0. Now, might be the value of classical bit 0, 1. For example, if I measure this as well. So this guy will be in my classical bit 1. What can be the answer of classical bit 1? Can anyone say that? Can anyone say what might be the answer for classical bit 1? We don't know. Why? Because 0 or 1 can be the answer. So why? Because I applied a Hadamard gate, bringing my Q1 to a superposition state, right? So as I brought my Q1 to a superposition state, so I am applying an X operation here. Why? Because here my control is 1. My control becomes 1 ka ikkada because I applied X gate. So once I applied an X gate, my control became 1. So as my control became 1, I need to apply an X operation to my Q1 as well. My Q1 is in superposition state. It's in a plus state. So if you apply X gate to your plus state, what is the output? The output is a plus state only. So that's what I mentioned, right? 0 plus 1 by root 2. Apply an X gate. The output will be 1 plus 0 by root 2. The output will be 1 plus 0 by root 2. Okay? So this will be the particular output for this thing. So that's why both of them are considered to be equal. So now, when I go 1 plus 0 by root 2 or 0 plus 1 by root 2, the output will be in this form. That is, it has 50% probability of being 1 and the remaining 50% probability of being 0. So that's why we don't know what might be the output. The output can be 0 or 1. We can't say that. Why? Because both are of 50% probability. Okay, if the both of them are 50% probability, we don't know what might be my actual answer. ఒకవేళ 70, 30, 80, 20 ఉంటే I can say what might be my actual output. But when I am having a plus state or when I am having a minus state, the 0 as well as 1, both of them will be the probability of 50 percentage on. As both of them are at a probability of 50 percentage, I cannot directly catch the actual output. Understood? So thereby we don't know what might be the answer. It can be 1 or 0 equal. Okay? So this is my classical bit. My classical bit stores the information. Once a measurement is done. Okay? Once a measurement is done, then I want my information to be stored in a classical bit only. I cannot store my information in a quantum state once the measurement is done. That's what I told in a yesterday session as. Okay, once you are measuring a quantum state, what happens? It loses its quantum nature and the value will be stored in a classical state or a classical position. Understood? So that's what will happen here. Now, I will talk about one another thing which is known as Bell measurement. Okay, let's talk about one thing called as Bell measurement. What is this Bell measurement? Very simple. In order to measure the Bell state, we have this Bell measurement thingy. And Bell measurement is very simple. That is the pure opposite of my 5 plus state logic. Okay. So that is how I can create a 5 plus state. Can anyone say that? Hadamard gate and C not gate. Okay. First I'll apply a Hadamard gate and then I'll apply a C not gate. So when I apply Hadamard gate and then when I apply C not gate, I will be creating a 5 plus state, right? Now, Bell measurement is an inverse of this operation. Bell measurement is purely an inverse of this operation. That is, first I will apply C naught gate First, I will apply C naught gate, and after applying C naught gate, I will apply a Hadamard gate. So that, and then I will measure it, and then I will measure. Okay. So this is my bell measurement. So this is what is known as a bell measurement. Okay. Apply C naught gate first, and then apply a Hadamard gate, and then you measure that qubit. So that is called as a bell measurement. Okay. So we'll be using this bell measurement in the super dense coding as well as quantum telephonics. Now, now one more thing about the bell states. So how I can exactly say that bell states are of a different phenomena or something like that? Very simple. So that is there is something called as a CHSH inequality. Okay, there is something called as a CHSH inequality, which directly says a simple sum. That is, when I'm having two qubits, okay, so and when I'm trying to find a probability of those two qubits or something like that, that's a big equation. We don't need that explicitly, but simply to put, let us consider you're trying to find a probability of two qubits or something like that. Then, or two pieces of information, simply to put, not two qubits, two pieces of information if they are following the principles of classical world and if they are limited by the principles of world's physics or something like that, the inequality is always this. Okay? The inequality is always lower than or equal to 2. Got it? But when you try the same inequality with respect to the quantum systems, that by using qubits, you get the value as 2.12 or something. Okay? So we are seeing this particular breakage of this inequality or particular violation of this inequality. And that's how we say that when two qubits are entangled in nature, they don't follow this classical limitations or the limitations of this classical world, which are given because of this particular communication stuff. That is, for communication, we ensure that the information should definitely travel at a speed of like something which is approximately equal or lower to the speed of light. So that is one of the limitations. So if two bits of information or two pairs of information values on that inequality is lower than or equal to 2, the meaning is that it is following that particular classical rules. Anya. But if you are doing the same thing with respect to quantum systems or qubits of information, then what is happening is that this violation is being violated. Why? Because if you find a probability, it will be something like 2.12 or something nearer to that. But definitely higher than my given inequality, that's my 2. Understood? So that's one of the inequality which we'll be seeing. Okay? Now, now let's go to the superdense coding concept. Now let's go to the superdense coding concept. So what exactly will happen in this superdense coding concept? Very simple and very straightforward and very easy, honestly to put. That is, this superdense coding is a very simple phenomenon, and the advantage is also not that huge of an advantage or some. It's a normal advantage only, but this can be extended to be a practical use case. But the thing which we are trying to show right now is a simple stuff. It's not that complete science fiction type of advantage or anything, but comparatively it provides better one than the existing one. But on expanding or on extending, we can see a huge advantage here. That is, for example, so these are two sets of information, right? Or I can say two pieces of information. So 0 and 1 are two pieces of information. So if I want to send two pieces of information through a classical phenomenon, how many bits do I need? I require 2 bits. So in order to send these two pairs of information, I require 2 bits of information or 2 bits of anything like, or I can say 2 bits. Classical. Okay. But by using the supertext coding, what happens is that I can send these two pieces of information by just using a single qubit. So that's the primary concept of this supertext coding thing. Okay. So simply to put, I can send a two pieces of information by using a single qubit, which classically takes 2 bits to send that particular. Okay. And how this exactly works? It works in a very simple and a very straightforward. It's a very easy concept actually. So simply to put, okay, simply to put a phenomenon goes like this. That is, for 2 power n bits of information or 2 power n pieces of information, for 2 to the power of n pairs of information, I require 2 power n bits and n qubits. So this is the one which is being represented by supertense code. Okay, this is the one which is being represented by my supertense coding calls. But in order to show the stuff at this point of time, we are simply using 2 bits and 1 qubit thing. Okay, that is for 2 to the power of 1 information, we require 2 to the power of 1 classical bits, but only 1 qubit. Okay, so this thing is shown by my supertense coding calls. Like how exactly we're gonna perform this supertense coding? Sorry? Okay, approximately for example, if you're using 2 to the power of n bits information, info, we require n qubits typically. So that is, for example, let us consider I want to send 4 pieces of information. I just require 2 qubits. 8 pieces of information, I just require 3 qubits. But classically, for 8 pieces of information, I will be needing 8 bits. So that's the difference. Now, so how are we exactly trying to do that particular stuff? So it actually works in a simple circuit manner and a simple entanglement concepts and everything. But the primary deal goes like this. That is, my B should measure the particular encoded qubit. So what exactly is the concept is? First thing, there will be 2 qubits or 2 pieces, Alice and Bob. Okay, these two guys have the entangled qubits with each other. So that is Q naught and Q1. These qubits are entangled to each other. Okay, that's my first concept. But Alice and Bob has 2 qubits, and these 2 qubits are entangled with each other, and they both share an entangled pair. So, and then what happens is Alice encodes the 2 bits of information in Q1, Q naught. Alice encodes the 2 bits of information in Q naught. That's the second. Okay, first deal is they both will share an entangled pair. And after they share an entangled pair, what happens? My Bob has Q1 and my Alice has Q0. Okay? And then what happens is that Alice will encode the 2 bits of information to his own qubit. Okay? That is how he's encoding that based on a type of message he wants to send. He will be using a particular gates. And by using those particular gates, he will encode the information. What are those gates? We will see right now. Okay? And third deal is after encoding, so he will be having this Q naught thingy, right? So initially he has a Q naught, Alice has a Q, and then he will be sending 2 bits of information. He wants to send a 2 bits of information. So he will encode these 2 bits of information in his Q. Okay, so based on the type of information which he want to send, or based on what he want to send, he simply encode that into his qubit, into the Q. And then he will be sending this Q naught to Bob through a classical manner. So through a classical system, he will be sending this Q naught to Bob. Okay. So my Alice will send Q naught to Bob using a classical channel. Using a classical channel, my Alice will send the encoded Q naught is there, the encoded Q naught qubit. So he'll be sending this encoded Q naught to the Bob through a classical channel. So I don't need quantum channel there. I'll directly give this Q naught information to my Bob. Now what happens? Bob will perform bell measurement. Bob will perform this bell measurement on the received Q. Bob will perform the bell measurement on the received. Doing the bell measurement, the output which he is getting will be the 2 classical bits of information which my Alice wanted to send. Got it? So this is a super dense coding concept, simply to put. So first thing is Alice and Bob will be there. So they both will share an entangled qubit. So that's the first. So Alice has Q naught and Bob has Q. And these two things will be entangled to each other. And it will Alice will okay. So these two things will be entangled with each other. Alice will have Q naught and Bob will have Q. Second stage where Alice wants to send 2 pairs of information to Bob. Right, that's the entire concept. Alice wants to send only 2 bits of information to Bob. So what Alice will do, he will try to encode these 2 bits of information into the qubit which he's have. So by using the gates, okay, what gate and all I will tell right. By using the type of gates or based on the type of information which he wants to send, he will use some gates to encode that information, and then he will send that encoded qubit to Bob by using some classical measures. By using a classical measure, he will send this encoded qubit. And then Bob will receive that encoded qubit, right? After Bob receives that encoded qubit, he will simply try to perform the bell measurement on that received qubit. Okay, after getting that encoded qubit, he will simply try to perform the bell measurement on that received qubit. And after performing the bell measurement, he will get a particular output, right? That output will be the information which my Alice wants to send. Got it? So in this way, Alice can send 2 bits of information by just using a single qubit. Okay? So in order to send 2 bits of information, we require 2 bits, I mean 2 pieces, right? But instead, in this supertext coding, Alice just sent only 1 qubit. Yes or no? Alice sent only 1 qubit, meaning he sent only one physical stuff or one component. So in this one component, he is having those 2 pieces of information. Got it? By sending this one component itself, my Alice is sending my Bob 2 pairs of information. So this is what will happen in superdense coding, simply to put. Understood everyone simply? The overview. I hope everyone understood the overview simply. Got it? So this is the concept of this superdense coding thing. Excuse me for a while. Now, so what exactly will happen in the second step? So why? Because the encoding the information is an important deal actually. So that depends on the gates what we are using. Okay. So when I say 2 bits of classical information, what can be the information? The information can be 00 S 01 10 or 1. So these are the information, right? The gates will look simply like this. For 00, he will apply an identity gate. For 01, he will apply an X gate. For 10, he will apply a Z gate. And for 11, he will apply a Y gate. Got it? So in this way, for a piece of information, he will be okay. Wait. Comes in reverse order. Yeah. For 01, we will apply Z gate. And for 10, we will apply X gate. So in this way, my Alice encodes that piece of information which he want to send to Bob account. Got it? Now, how the quantum circuit looks like for this particular thing? No. This is a by default trait. It's a by default trait. So that both parties encoding, which we'll be seeing in BB84 protocols and stuff like that. Now, how does the quantum circuit looks for this particular thing? And they're very simply to put. First thing is we will try to encode these two data. Or first, let's try to create a circuit. Yes, that is Q naught and Q1. First, first thing is what we will be doing is we will entangle these two qubits. That's my first option. So how I can entangle the qubits? By using the Hadamard gate in the first place, and then I will use the C naught gate again. So when I use a Hadamard gate followed by a C naught gate, I am entangling the qubits. After entangling the qubits, what will my Alice do? She will try to encode the information. Now let us consider Alice wants to send 1 1. Let us consider Alice wants to send 1 1. So at that time, what she will do? She will simply encode the Q naught by using Y. Okay, she will simply encode this particular Q naught bit of information by using the Y. On using the Y gate, my Alice simply encoded that 1 1 information to my qubit. Now, after doing this operation, what it will try to do ante, Alice will send this. Okay, so entanglement means both of them will be correlated. So it will not be applied to a single qubit. Now, after doing this encoding, my Alice will try to send her encoded Q naught to Bob. Okay, by using a classical channel, like anything, any classical channel. So here some classical simulation will happen where my Alice is sending Q naught to Bob. Once my Bob receives this Q naught, what he will do at that? He will perform the bell measure. What will happen in a bell measurement? Simple. First, he will apply a C naught gate and then he will apply a Hadamard gate. So this is my bell measurement. The reverse of the entanglement thingy which we are doing. The reverse procedure of the entanglement thing which we are doing is my bell measure. Okay. So my Bob will apply a C naught gate and then will apply a Hadamard gate through which he is applying a bell measurement. And then what he will do, he will simply measure it. He will simply measure. Got it? So after doing the measurement thingy, that is after applying the C naught gate and then applying the Hadamard gate, he will simply measure that particular stuff. Okay, he'll simply measure that particular qubit. And let's say stored is C0. And this C0 has the two bits of information which he wants to send. Got it? Or I can say this particular measurement. So what C0, so he would perform 0 and 1. And that దగ్గర ఇప్పుడు 2 qubits ఉంటాయి కదా. So one thing is a qubit which he himself is having, and one thing is the one which he is receiving one. So yeah, I'm just displaying this particular thing like C0 and C1. That's it. So this C0 has one information, the C1 will have one other thing. So in combination of these two will give rise to the message which Alice is trying to send to Bob. Got it? So in this way, my Alice is able to send two bits of information or two pieces of information to the Bob by just simply sending only one qubit. So only Q naught is being sent to my Bob, right? By just only sending the Q naught to Bob, he is giving two pairs of information. So this particular concept is known as superdense coding. Got it? Got the concept of superdense coding, everyone? Okay. So okay. So for example, if we are doing a different type of entanglement ankunda, like so this creates a one-one state, obviously. So let us consider here we are using some 5 minus state ankunda. So meaning ఇక్కడ నేను z పెట్టిన. So if I keep a z here, it will become a 5 minus state. So at that time, I will encode my information in a different format. So these gates are there, right? This 00011011 gates, K encoding concept, right? This works for 5 plus n time. Yeah. This works for 5 plus type of entanglement which we are doing. So are they, for example, if we are encoding in a different form, then we'll be having a different case coming into. Okay, in that case, it's simple. Actually, instead of using the Y gate, you'll use the X gate. That's it. So that is simply to put, let's put it in this way. No, okay, okay. I'll say. So this H and C naught. This is the one. Uh, this one. Okay, that's this thing is a type of information which Alice wants to send to Bob. It does not have a reflection on the entanglement which we are doing. Alice wants to send two pairs of information to Bob, right? So these are the four options for that two pairs of information which she wants to send. Let us, this example is Alice wanted to send 1 1 to Bob. That's why she used Y gate. If Alice wants to send 0 1 to Bob, instead of this Y gate, she will be using the Z gate. Yeah, that is the entire reason for this HDC also coming into play. So that is here I am having 5 plus, right? The moment I keep a Z gate here, this entire thing will become a 5 minus state. And after this 5 minus state happens, my that Z will represent the 5 minus state. If we do not have this encoding concept, then that's it. But here the main deal is sending the piece of information కాబట్టి we are doing it this format. ఏ కాదు అది వేరు అది డేటా ఎన్కోడింగ్ లోకి లెక్క వస్తుంది దిస్ ఇస్ సింప్లీ ద ఎస్డిసి ఎగ్జాంపుల్ దాట్స్ ఇట్ బట్ నార్మల్లీ వెన్ యూర్ టాకింగ్ అబౌట్ డేటా ఎన్కోడింగ్ వీ హ్యావ్ యాంప్లిట్యూడ్ ఎన్కోడింగ్ బేసిస్ ఎన్కోడింగ్ అండ్ యాంగిల్ ఎన్కోడింగ్ దాట్స్ డిఫరెంట్ approximately yes but that's not a complete thing. Yes. Yeah, okay. Yeah, approximately yes. Yes, 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 that's correct. So if you want to show the classical data in a quantum phenomenon or a quantum representation, we'll be using gates only. So by just using the gates, we can simply encode the information as. But for that, we will be having a different type of formats. We can't use this IZXY gates for that. We'll be having a different system and different stuff and everything comes into play. This is basic level. So that's why SDs is a basic level. So that is why super dense coding is a very basic level. Advocate. So that gives rise to this information encoding concept. Like if Alice wants to send these two bits of information, she simply can use only these bits or these keys. She don't need to perform the complete encoding and stuff like that. She can directly use these gates and she will get she will make that encoding done and she will send the qubit directly. Yes. But in application level, you will perform, there are three types of encoding called as angle, basis, as well as amplitude encoding. For them, you need to do a lot of stuff. Like you need to do the feature mapping, that, this, and all. And then you'll be having that encoded state. Yes. There's a basic concept of how you can represent the classical data in quantum. Like, yeah, optical fiber cable, or you can say waves or anything. So any type of classical phenomenon you can use to send the information. In this case, not a problem. That's what will happen in HDC. Once my Alice encodes the qubit and everything is proper, she will send this encoder qubit to Bob by using a classical channel. Classical channel means any type of classical phenomenon you can use. It's not only a quantum thing. You can use any. And once the Bob receives that qubit which Alice is trying to send, he will perform this Bell measurement. After performing the Bell measurement, he will simply measure the qubits which he is having, thereby giving a final. Got it? And this is how HDC works in a very simple way. And this gives the basic rise to my data encoding concept. Basic of data encoding, like the very basic form of how I can represent the classical data in quantum. This is how I can do it. Okay? So this is the concept of HDC and everything. Now, there is one more concept which is called as quantum teleportation. So, very simply to put, this quantum teleportation is not something new or fully out of science fiction or anything. ఏమి టెలిపోర్టేషన్ ఏం అవ్వట్లేదు బట్ వాట్ ఈస్ మీన్ బై టెలిపోర్టేషన్ సింప్లీ టు పుట్ sending an information to one place to another place without actually using any channel or without actually sending some. అంటే ఏలో 10 అని ఉంది అనుకుందాం. నేను ఆ 10 ని బికి ఇవ్వకుండానే ఆటోమేటిక్ గా బిలో 10 అని వచ్చేయాలి. అది నా ప్రైమరీ కాన్సెప్ట్ ఇప్పుడు. And that is what entanglement is. And that's what we are trying to do here. For that thing, we will be having this quantum teleportation concept. Without actually sending something, I will represent a complete information in my another cube. How I will be doing? Very simple. So this also has a lot of things. SDC కన్నా ఎక్కువ ఉంటుంది but I will try to explain in a simple manner. That is, here we will be having three qubits. So in SDC we had only two qubits, right? Here we will be having three qubits. That is why something called as qubit Q, qubit A, and qubit B. I will be having three qubits here. My primary concept is to send the qubit from A to B. That's my primary concept. అంటే ఏత్ క్యూబిట్ లో ఉన్న ఇన్ఫర్మేషన్ బీత్ క్యూబిట్ కి తెలియాలి ఆర్ బీత్ క్యూబిట్ కి వెళ్ళాలి వితౌట్ యాక్చువల్లీ కమ్యూనికేట్ ఆర్ వితౌట్ యాక్చువల్లీ సెండింగ్ సమ్ ఓకే So if A has a quantum state as A, the output by B should be knowing this phi. So psi. Now B ki a psi A ante enti అని తెలియాలి. Without that psi A being actually going to my B. Without me actually sending something to my B's output should automatically be equal to psi. So how this thing will happen? Firstly, so here I am behind psi q. First thing what I will be doing is I will entangle my A and B. First thing is I will entangle my A and B in a 5 plus system. Okay, I will entangle my A and B. And then I'll just elaborate a brief on it. I'll just tell a brief on quantum teleportation. In tomorrow's morning session or in tomorrow's session, I will explain it in a way more deeper way. But simply, I'll just give a brief on it, like how exactly it will happen actually. Not how exactly also, but I'll simply tell what is the entire underlying concept. Because ఇది చెప్పి మళ్ళీ మీకు ఎస్టీసీ కన్ఫ్యూజ్ అయిపోతాం obviously. So both are completely both use different case for encoders. So that's why I'll just tell an overview on it. First, A and B share an entangled cube. That's my first case. Second case is I will perform some operations of Q and A. Q की A की मध्य कुछ operations जरूरताई as well as Q की B की मध्य कुछ operations जरूरत है. Okay. First case. A and B share an entangled state. Yes. First case is A and B will share an entangled state. That's my first. Second case is I will perform some operations of Q and A as well as I will perform some operations of Q and P. QAB కలిపి ఆపరేషన్ జరగదు. అసలు ఏకి పికి కమ్యూనికేషన్ అవ్వదు అనమాట. దాట్స్ మై ప్రైమరీ గోల్. సో మై ప్రైమరీ గోల్ ఇస్ నాట్ టు కమ్యూనికేట్ ఏ అండ్ బి. అలా కమ్యూనికేట్ చేయాలనుకుంటే నేను డైరెక్ట్ గా ఇన్ఫర్మేషన్ ఇచ్చేయొచ్చు కదా. బట్ నాకు కావాల్సింది ఏంటి ఏకి బికి మధ్య లింక్ ఉండకూడదు. బట్ ఏస్ ఇన్ఫర్మేషన్ షుడ్ బి గివెన్ టు బి. So that's my primary goal. So for that reason, I will perform some operations of Q and A as well as I will perform some operations on Q and B. And after these two operations are done, I will simply measure B and that measurement of B will be psi. That's the primary concept what will happen here. Okay, so what are these operations which we are doing? That one I will tell in tomorrow, sir. Because we will be having different case and different encoding techniques. But underlying concept is this particular phenomenon. A, B, and Q. Okay? A, B share an entangled qubit. Done. A has a state. A ఒక qubit state ఉంటుంది. Q ఉంటుంది. Q కి ఏదో ఒక qubit state ఉంటుంది. Q does not need to have any qubit state as well. Q కి దీనికి సంబంధం లేదు. అది జస్ట్ అలా ఉంటారంట స్పేస్ లో. Will perform some operations with Q and A. And we will perform some operations with Q and B. And then I will measure by B. And I'll be getting an output, and that output will be this psi of A. Got it? So in this way, the A's information will automatically be reflected to my B at the last stage. అంటే అన్ని ఆపరేషన్స్ చేసిన తర్వాత B ని మెషర్ చేసినప్పుడు నాకు అవుట్పుట్ ఏంటి ఏ ఒక స్టేట్ నా అవుట్పుట్ లో వచ్చేస్తాను. ఎలా వస్తుంది? బికాస్ ఆఫ్ దీస్ ఆపరేషన్స్. QA operations as well as QB operations. But there will not be any connection between A and B. A కి B కి మధ్యలో ఏ టైప్ ఆఫ్ కమ్యూనికేషన్ జరగదు. యాజ్ వెల్ యాజ్ ఏ ఒక స్టేట్ ని Q కి కూడా ఇవ్వదు. అలా అంటే నేను ఏని Q కి ఇచ్చి Q B కి ఇవ్వచ్చు కదా. అది కూడా ఉంటుంది. బట్ అలా కూడా జరగదు. A will not send any information to anyone, even to Q. A will not send information to Q as. ఏ ఇన్ఫర్మేషన్ దాని దగ్గరే ఉంటది. Okay? But still, after these operations, my B will have that information to it. Got it? So that's why the concept of teleportation. Else I can simply say concept of passing. సో నాకు ఎవరికైనా గొడవ అయింది అనుకో, నేను మీకు ఏమైనా ఇవ్వాలనుకున్నాను అనుకో, నేను నా ఫ్రెండ్కి ఇస్తాను, వాడు మీకు ఇస్తాను. సింపుల్. It's not teleportation, it's passing, right? But here the passing also will not happen. Here the teleportation will happen, meaning this A's information will not be sent to anyone. ఏ దాని దగ్గరే ఉంచుకుంటారు ఆ ఇన్ఫర్మేషన్. But by doing these operations, that information will directly be going to P because of this entanglement nature. First thing, and second thing, because of this guy called Q. A Q to qubit of a state, that thing helps a lot in this operation. And what are those actual operations which we'll be doing, or what are the actual games which we'll be doing? All those things we can discuss in tomorrow's. Okay. So yes, if you're having any sort of queries, you can ask me, right? Um, uh, mm, okay. Is my voice audible to the end? Okay. So what happens is that in that particular concept, what did I mention here? I mentioned that Q0 is with Alice and Q1 is with Bob. These two are entangled with each other. That's it. అలాగనే రెండు ఒకే స్పాట్ లో లేవు. ఒకటి ఆలిస్ దగ్గర ఉంది, ఇంకోటి బాబ్ దగ్గర ఉంది అనమాట. ఓకే. సో లెట్ us consider we both are there. I am in Chennai and you are here. So what will happen is that I will be having my Q0 and you will be having your Q1. So I will encode my information to this Q0 and then I will send that encoder Q0 to you. That's it. అంటే నా దగ్గర ఉన్న క్యూబిట్ ని నేను నీకు పంపిస్తాను. నీ దగ్గర ఆల్రెడీ ఒక క్యూబిట్ ఉంది కదా. సో ఇన్ దాట్ వే యూ విల్ పర్ఫార్మ్ ది బ్యారిమేషన్. Already you are having one qubit with you. I am having one qubit. I encode the information to my own qubit. And then I will send that qubit to you. Right now you are having how many qubits? How many qubits I sent you? That's okay. That one we can send easily అండి. క్యాషువల్ నార్మల్ గా ఇప్పుడు వేవ్ ని పంపించినట్టే పంపించవచ్చు. అక్కడ ప్రాబ్లం ఉండదు. ఆ లైక్ ఆప్టికల్ ఫైబర్ రూపంలో పంపించవచ్చు, లేదంటే సిగ్నల్స్ రూపంలో అయినా పంపించవచ్చు. ఆ మాడ్యులేషన్ మళ్ళీ మీకు డిఫరెంట్ కాన్సెప్ట్స్ వస్తాయంటే. సో అక్కడ మీరు ఏదర్ లేసర్స్ ని యూస్ చేసుకుని మాడ్యులేట్ చేయొచ్చు, ఎలక్ట్రికల్ సిగ్నల్స్ ని యూస్ చేసుకుని చేయొచ్చు, మ్యాగ్నెట్ ని యూస్ చేసుకుని చేయొచ్చు, టెంపరేచర్ యూస్ చేసుకుని చేయొచ్చు. దట్ కమ్స్ అండర్ డిఫరెంట్ టైప్స్ ఆఫ్ క్వాంటమ్ కంప్యూటింగ్. Yes, that depends on the type of qubit which you're actually using. అంటే క్యూబిట్ అవ్వట్లేదు. అంటే క్యూబిట్ నేను ఎక్స్ప్లెయిన్ చేస్తాను లాస్ట్ 2 days కానీ లాస్ట్ డే అప్పుడు ఎక్స్ప్లెయిన్ చేస్తాను. యూస్ మైక్. Yes, correct. So using qubits is obviously an optimum manner theoretical. But why we are not exploring in that space and very simply to put, I can represent a qubit physically as well, but I cannot represent a qubit physically at this point of time. So meaning by using topological quantum computing, I can represent qubit, but that is a complex process. ఇంకా చేయలేదు. That's still in research thing. Yeah, a qubit అనేది physical గా నేను రిప్రజెంట్ చేయలేకపోతుంది. So for that reason, we are still trying to improve the qubit to an extent so that qubit can take the steps again. So that's how the concept works.
Yeah, often transformation there are surgical errors also.
Yeah.
Yeah. So further we need to on whether or like uh, counter attacks. Attacks are also possible during the transmission of the tumor.
Yes. Yeah. So first thing is that's why we are having something called as error correction codes. So obviously when you're sending an information or sending an దాన్ని మీరు normal గా if you're using that information also you'll be getting a lot of errors in this quantum thing. A quantum circuits may you'll be having a lot of errors which comes into play. So for those reasons, we were having something called as error correction codes and error correction techniques. So ancillary qubits are ఒకటి వాడతాం అన్నమాట అక్కడ. So they are the extra qubits which we are using to protect the logical state of that qubit.
And that's what the and from handling noise and in the box itself. But what I must keep code after we on that transmission, what we get some errors with that.
Okay, so after transmission, if we get an any error, that guy can also implement the same techniques. That's first thing. Second deal is if you want to secure your communication, for that you can use a cyber security techniques. So these two can be used in those cases actually. Protocols, just a simple protocols. That's it. And extra cyber security layers ఏం వెయ్యం. Protocols యూస్ చేస్తాం. PB84 కానీ E91 కానీ లేదా శాటిలైట్ సెక్యూర్ ప్రోటోకాల్స్ కానీ సో ఆ టైప్ ఆఫ్ ప్రోటోకాల్స్ ఉంటాయి అది వాడతాం ఫర్ సెక్యూర్ కమ్యూనికేషన్. ఎనీ ఫర్దర్ క్వైరీస్ టు ఎనీవన్? Okay, I guess there are no further queries. Bro is having yes.
Currently, there are two proven technologies reliant on this. So, is there any chance or how would it are making it quantum?
Hmm.
Okay.
Okay, nice one. Yes, please. So that is oh one more. Okay, so that is so when you're talking about AI, we are simply talking about optimization, honestly to put. So why? Because AI is nothing but doing something on its own. So when it does something on its own, it should have that knowledge to seek that is the correct answer. Right? So simply to put, not by talking like AI with quantum or stuff like that, we can simply use this quantum to find the best answer in a quick manner. Your AI is what simply to put, let us take ChatGPT. What will happen in ChatGPT simply? Text generation. We think it's text generation. But what exactly is happening in ChatGPT? Ante, I will say one word. The prediction of the next word is happening. Simply to put, the complete stuff is not being generated in a single go. So when I say one word, the next word is being predicted. So ante, out of all the corpus it is having, it is deciding what is the next word should be. That's what will happen in AI, simply to put. అంటే నెక్స్ట్ ఏంటి అసలు క్వశ్చన్ ఒక ఆన్సర్ ఏంటి అని కనిపెడతారు అన్నమాట. సో ఈ కనిపెట్టే ప్రాసెస్ లో మనం క్వాంటమ్ కంప్యూటింగ్ యూజ్ చేయొచ్చు. సో ఐఎమ్ నాట్ సేయింగ్ దట్ క్వాంటమ్ విల్ కంప్లీట్లీ రిప్లేస్ AI. ఆబ్వియస్లీ కంప్లీట్ రిప్లేషన్ ఉండదు. బట్ ఇన్ దిస్ టాస్క్ టు సర్చ్ ఫర్ అన్ ఆప్టిమమ్ ఆన్సర్ వీ కెన్ యూస్ దిస్ క్వాంటమ్ సిస్టమ్స్ టు డూ దట్ ఇన్ ఎ ఫాస్టర్ అండ్ ఎఫిషియెంట్. దాట్స్ ఇట్.
So, what is like integrating quantum in AI? People want to do AI in quantum. Like if I'm doing a project of responsibility Meaning, in quantum, how do we implement AI in the quantum?
Okay, so implementing AI in quantum goes in a very simple way actually, but the actual implementation is hard. But for now, you can use like this because a quantum state of output ఉంటారు కదా, that will be a lot of values coming into play. So especially if you're using optimization, so you'll be having a lot of solution states. Out of all those solutions, say it directly depends on the energy for a particular output. But మీకు అన్ని తప్పైనా కూడా ఎనర్జీ చాలా తక్కువ ఉంటారనమాట. లైక్ అన్ని జీరోస్ ఉన్నాయనుకోండి, ఎనర్జీ విల్ బి వెరీ లో. సో ఐ కెనాట్ మాన్యువల్లీ ఫైండ్ ఆర్ ఐ కెనాట్ మాన్యువల్లీ చెక్ దాట్ పర్టిక్యులర్ ఆస్పెక్ట్. బట్ వాట్ మై క్వాంటమ్ విల్ డూ అంటే, ఇఫ్ ఆల్ ద అవుట్పుట్స్ ఆర్ జీరో ఆర్ ఇఫ్ ఆల్ ద వాల్యూస్ ఆర్ జీరో, ద టోటల్ ఎనర్జీ విల్ బి వెరీ మినిమం. సో వాట్ మై క్వాంటమ్ విల్ డూ, వెరీ మినిమమే నా బెస్ట్ ఆన్సర్ అని చెప్పి ఇచ్చేస్తుంది నాకు. బట్ అన్ని జీరోసే ఉంటాయి అక్కడ, రైట్? సో ఫర్ దిస్ ప్రాసెస్ యూ కెన్ యూస్ ఏఐ. యాక్చువల్ వి ఆల్రెడీ డిడ్ దట్. అంటే ఏంటంటే డ్యూరింగ్ ఆప్టిమైజేషన్ టాస్క్స్ ఇన్ అ సొల్యూషన్ స్టేట్, in order to identify the perfect vector with a perfect energy amplitude or perfect energy value, you can use AI. That's first deal. And second deal is for natural language processing also. That is, we conducted a research for quantum generative transformers in IBM. So in those cases as well, we can use this particular thing. అంటే ఏంటంటే నెక్స్ట్ వర్డ్ క్వాంటమ్ ప్రిడిక్ట్ చేస్తారు ఏదో ఒకటి. ఆ ప్రిడిక్షన్ ఎంతవరకు కరెక్ట్ గా ఉంది, ఇంకా బెటర్ గా ఏమైనా రావచ్చు అని చెప్పి మనం మళ్ళీ ఇదే ఏఐ యూస్ చేయొచ్చు. సో దాట్స్ హౌ యూ కెన్ ఇంటిగ్రేట్ ఏఐ ఇన్ టు దిస్ పర్టికులర్ కోడ్.
Okay, from that you have the like videos, yeah, from the very optical.
Okay, AI to generate an optimized quantum circuit is a hard task, actually. That's still in research process. That too is a complex task. ఎందుకంటే optimizing a quantum circuit by using classical AI is not that feasible at this point of time. So that's actually a research area. You can focus on that as well because optimizing a circuit is actually a hard task. And AI also can't do that. ఇంకా చాలా couplings and decouplings ఉంటాయి మధ్యలో. We did not use that particular phenomenon actually.
Thank you. The bottom of SDC, you have mentioned you are using some gains in mind is no angle. Like with the word encode similar to the
No, encode is not equal to encryption here.
so for we will be using stealing data.
Yes, yes, he can steal the data because we are not using any type of security protocols when talking about SDC. So if you want to secure or if you want to send a secured piece of information, then we will be using a security protocol. But the SDC is completely about what? Instead of sending n bits of information, sorry, instead of sending 2 power n bits of information, I will send it only by using n cube. That is my primary concept of SDC. Other if I want to talk about secure, then I can use BB84 or I can use E91 or I can use secure satellite communications for that. That's a different protocol. దానికి దీనికి సంబంధమే లేదు actually.
Okay, thank you. Algorithm on this data. So because we transmitting it to the instrument much.
Yes, actually we can do that, but అది అంత efficient గా ఉండదు. అదే primary concept. It can be that efficient.
How does transpiler optimize the circuit, sir?
పెద్ద కాన్సెప్ట్ అది. చాలా పెద్ద కాన్సెప్ట్ అది. అది అసలు లైట్ అయితది. ఆ! సో, ఆప్టిమైజర్ అంటే అదేంటంటే మొత్తం ఆప్టిమైజ్ ఏం చెయ్యదు. మొత్తం సర్క్యూట్ మనమే బిల్డ్ చేస్తాము. దాని నుంచి బెస్ట్ వాల్యూస్‌ని తీస్తారనమాట. దట్స్ ఇట్. ఇట్ విల్ నాట్ ఆప్టిమైజ్ ద సర్క్యూట్. ఇట్ జస్ట్ టేక్స్ ఔట్ ద బెస్ట్ వాల్యూస్ ఫ్రమ్ ద వన్ విచ్ వి ఆర్ యాక్చువల్లీ బిల్డింగ్. మనం రెడీ చేస్తాం సర్క్యూట్‌ని. మనం రెడీ చేసిన సర్క్యూట్ నుంచి ఏది కరెక్టో తీస్తది గానీ, ఓవరాల్ ఆప్టిమమ్ వాల్యూని తీయలేదు. ఆ ఓవరాల్ ఆప్టిమమ్ తీయాలంటే మనం సర్క్యూట్ రెడీ చేయాలి. అక్కడొస్తది కాన్సెప్ట్. అది ఎలా తీస్తదన్నది కొంచెం పెద్ద కాన్సెప్ట్ అది యాక్చువల్లీ. ట్రాన్స్‌పిలయింగ్ ఎ సర్క్యూట్ ఈస్ ఎ బిగ్ కాన్సెప్ట్. ఇంకా నీకు ఎనర్జీ లెవెల్స్, ఫిజిక్స్ ఇవి ఎక్కువ ఫిజిక్స్‌కి రిలేట్ అయ్యి ఉంటది యాక్చువల్లీ. But this is how it will happen. It will not directly optimize the circuit. From the circuit we built, it gives the possible value. That's it. చూద్దాం. పెద్ద కాన్సెప్ట్ అది యాక్చువల్లీ.
Any further questions? I think your voice is right. Clear. Yeah. Right. So, as a place to get access your particular content data. So how we can learn from that particular thing?
This comes under different. Okay, simple. See, so you ask two different questions. First question is how I can say encoder is different from encryption. Second question is how I can identify. How I can identify is very easy, very simple. Let us consider. Uh, okay, okay. Let us consider I have an Oriental. Okay, so 100% love cinema చూసావు కదా. సో దాంట్లో అతను ఏం చేస్తాడు మార్కర్ పెన్ను తీసి అట్లా పర్ఫెక్ట్ గా పెట్టుకుని మళ్ళీ వచ్చినప్పుడు చూస్తే ఎవడో వచ్చాడు అని అంటాడు రైట్ హౌ హీస్ ఫైండింగ్ దట్ సమ్వన్ కేమ్ ఇన్ టు హిస్ రూమ్ కింద మార్క్ చేస్తాడు కదా ఆ పొజిషన్ డిఫరెంట్ గా ఉంటుంది సింప్లీ టు పుట్ సో ఇన్ సేమ్ వే వెన్ సమ్ అదర్ పార్టీ ట్రైస్ టు సీ మై డేటా విల్ గెట్ డిస్టర్బ్డ్ అన్నమాట ఓకే నా డేటా డిస్టర్బ్ అయినప్పుడు ఆ పంపించిందే నేను కదా సో ఐ విల్ ఈజీలీ ఐడెంటిఫై దాట్ పర్టికులర్ డిస్టర్బెన్స్ ఓకే లైక్ ఫర్ ఎగ్జాంపుల్ అండ్ నాయిస్ వచ్చినట్టు లెక్క లేదా ఆ ఎంటాంగిల్డ్ అనేది డీకంపోజ్ అయిపోతుంది వెంటనే ఆ డీకంపోజ్ అయినప్పుడు ఇట్ విల్ నో లాంగర్ బి క్వాంటమ్ ఒక నేను పంపించిన ఇన్ఫర్మేషన్ లేదా నా దగ్గర ఉన్న ఇన్ఫర్మేషన్ క్వాంటమ్ గా ఉందా క్లాసికల్ గా ఉందా అని చెప్పి నాకు ఈజీగా కనిపించేస్తుంది బై సీయింగ్ ద వేవ్స్ అండ్ ఎవ్రీ ఒకవేళ నాకు వేవ్స్ మొత్తం సడన్ గా నాశనం అయిపోయి ఒకే ఒక పాయింట్ పడిపోయింది అనుకో దాని మీనింగ్ ఏంటి డెఫినెట్లీ సమ్ అదర్ గై సా మై డేటా అని అర్థం right? So in that way, will I easily identify that if any other guy sees my particular. Now, encoding and encryption and encoding is nothing but representing one thing in a different format or different point of view. Okay, encryption ante encoding in order to secure your information is encryption. Okay, encryption is a form of encoding, but encryption is not equal to encoding. Encoding ante enti ఫర్ ఎగ్జాంపుల్ మీరు ఇక్కడ ఉన్నారు నా పాయింట్ ఆఫ్ వ్యూలో ఒకలా కనిపిస్తున్నారు కదా అక్కడి నుంచి లైక్ ఆ కార్నర్ నుంచి ఉన్న వాళ్ళకి ఇంకోలా కనిపిస్తారు సో దట్ ఈస్ ఎన్కోడింగ్ మీనింగ్ ద సేమ్ ఇన్ఫర్మేషన్ ఇన్ ఎ డిఫరెంట్ పాయింట్ ఆఫ్ వ్యూ ఆర్ ఇన్ ఎ డిఫరెంట్ ఫార్మెట్ ఆర్ ఇన్ ఎ డిఫరెంట్ డొమైన్ సో దట్ ఈస్ ద కాన్సెప్ట్ ఆఫ్ ఎన్కోడింగ్ సింప్లీ టు బట్ ఎన్క్రిప్షన్ ఇస్ వాట్ నేను మొత్తం గోడలు కట్టేసి మీ చుట్టూ ఒక బ్లర్డ్ ప్లేట్ వేసి అన్ని వేస్తే బయట అసలు మిమ్మల్ని చూడడానికి అవ్వదు దట్ ఈస్ ఎన్క్రిప్షన్ meaning I will encode you in such a way that the other guy can't see you. Got it? So this is the difference between encoding and encryption. అర్థమైందా? Okay.
Process of how the arrange the report and how to decrypt it. And we need to answer the secret that.
This one, oh my god. ఇదువా ఇది this only, yeah? Z. Hey, this is easy, bro. So simple. So firstly, I will entangle my qubits. Once after I entangle the qubits, what will happen? For example, నేను 0 1 పంపాలనుకుంటున్నాను అప్పుడు నేను జీ గేట్ వాడతా ఇక్కడ దట్స్ ఇట్ నేను కనుక 1 1 పంపాలనుకున్నాను అనుకో వై గేట్ వాడతా ఓకే ఇట్స్ అ టైప్ ఆఫ్ గేట్ విచ్ ఐ షుడ్ బి యూజింగ్ స్టాండర్డైజ్ థింగ్ మనం ఏం చేయలేము అక్కడ అండ్ నేను 0 0 పంపాలనుకున్నాను అనుకో I identity gate వాడతాను. That's it. It's a type of gate which I should be using to send a piece of information. That's it.
Thank you very much. We have a wonderful sessions yesterday, and we will continue for 4 more days. All with you. So, particularly regarding today's session, so I'd like to request our website full mail, one mail, say about few words, then the feedback. Thank you so much for giving how much energy. Maybe I can say on behalf of all of us today.